So if we want to solve Laplace's equation in the upper half plane and the boundary conditions are piecewise constant, so that means that you've got a constant value along this boundary here of phi 0, then it changes at x1 to phi 1, then it changes at x2 to phi 2, and so on up to xn, after which it's phi n. So we have that situation, piecewise constant boundary conditions. Then instead of using the Poisson formula for the half plane, we can use something which is much easier, which is this formula here. One small thing we have to be careful about is this argument here. So this argument, we choose to make the branch cuts, so the argument is going to have a sudden jump somewhere. We don't want any sudden jumps in the region we're interested in. So what we actually do with the argument is unusually we choose to have the branch cut in the negative pi by 2 direction. So the branch cuts associated with these changes are out of the way in the negative imaginary direction. Okay, so where does this formula come from? Well, it's maybe not quite obvious, but what we do is we first note that if we write down something of this form, but don't just put constants in we don't know yet. So if we write down this, so it's 1 over pi plus j equals 1 to n of, and then some other unknown constants, so I'll just call this a j and argument z minus x, sorry, it should be xj. Where, and we have to specify that a and b and aj are all real numbers. Then, if we also consider this function f of z, which I'm going to write down like that, so it's bi plus 1 over pi sum of j as before, and aj times log of z minus aj. Okay, so how are these two things connected? Where again with this log I choose the branch cuts to be at the theta equals pi minus pi by 2 direction. Okay, so how are these two things related? Well, if I consider the imaginary part of this, then what do I get? The a's and b are real. So the imaginary part of this will give me b, and the imaginary part of log, remember log of something is the modulus plus I times the argument. So the imaginary part of this is going to be precisely this. Now this is an analytic function in the upper half plane, because we've been careful about branch cuts. So if this is analytic, then that means both the real part and the imaginary part satisfy Laplace's equation. They're both harmonic. So this definitely satisfies Laplace's equation in this region. Now all we have to do now is make sure that this also satisfies the boundary conditions. Okay. So to do that, we notice what happens with what's going on with this arg z minus x. So if we're along the real axis, then the arg of z minus x, if we're on the real axis, is basically going to be equal to 0 if z is greater than x. So this is z is greater than x. So we're on the real axis always, and it's going to be pi. This is going to be a negative number. So if z is less than x, and what happens if z equals x. Then it's undefined, but we won't worry about those single individual points. Okay, so let's consider what happens when x, in this case, is greater than xn. Well, if x is greater than xn, then z is greater than all of the xj, so this will be 0. So for x greater than xn, we've just got, substituting in this boundary condition, so we've got phi n is equal to b. So b is equal to phi n, which is what we expect here. Then we just work along backwards. So we know what phi n is now. So now we consider what happens if x is less than xn, but greater than xn minus 1. Then we've got phi n minus 1 is equal to b, which now we know is phi n, and plus 1 over pi. Then basically what happens is we're going to have just one thing which is not 0. So we'll end up with the last term in this series not being 0. So we'll end up with a n here times pi. Okay, so this will give us the pi because we're between xn minus 1 and xn when j is equal to n. And there we have it. So then that gives us that a n is equal to phi n minus 1 minus phi n. And then we carry on like this. The sums sort of get bigger and bigger. So we do maybe one more. So if x is between xn minus 2 and xn minus 1, then let's draw that. So we've now got xn minus 1 and xn minus 2, and then here this is phi n minus 2. It's going to be equal to phi n plus 1 over pi. And then we're going to have to sum two things. So but both of those are going to give a factor of pi, but then it's going to be a n plus a n minus 1. So so a n we've already worked out is phi n minus 1 minus phi n, and then a n minus 1 is the thing we're trying to find. So you can sort of see a pattern emerging. These things are going to cancel, and this thing, we move on to this side, and therefore we get a n minus 1 equals phi n minus a n minus 2 minus phi a n minus 1. So you see the pattern's going to repeat, so this will hold in general.